Dr. Sue Niezgoda is a professor of civil engineering at Gonzaga University and a registered licensed engineer. She is currently working on monitoring the effectiveness of beaver dam analogs to reduce downstream sediment loads and restoring valleys to a stage zero channel network. Sue, thank you so much for taking the time today.
Sure. Thanks for having me. I'm excited to talk about beaver dam analogs and stage zero restoration. This will be great.
Awesome. Well, could you start by explaining what are beaver dam analogs?
Sure. Beaver dam analogs essentially simulate, they're man-made structures that simulate natural beaver dams. And so typically natural beaver dams do great things for the ecosystem in that essentially they store water, they retain sediment, so on and so forth. And beavers come in, of course, and build those beaver dams. And so through their great ecosystem engineering prowess, right? But there's instances and locations where the beaver are unable to survive, right? So the habitat isn't very good for the beaver in spot. They need wood and water. And so if there isn't any wood, and typically they use the wood to build their dams as well as their lodges, but also they eat wood. It's their primary food source. So if the wood isn't present, woody vegetation isn't present, then they won't be able to exist in that location. And often there's channel systems that don't have wood because maybe the channel has been straightened and incised and down cut and then pulled the groundwater table down and like essentially created a drought environment and vegetation has died off. In those particular type of river systems, if we can simulate the beaver dams to do similar processes to natural beaver dams, we're using beaver dam analogs, we can hopefully maybe bring back the hydraulics and the essentially raise the water table back up, create the ponding, raise the water table back up to connect it to the floodplain, and then also maybe get new vegetation planted and put in there, have that water feed that vegetation and get the wood back in. Then maybe the beaver will come and take over the beaver dam analogs for us, right? And then maintain them in the long term. So the goal is with beaver dam analogs is that you are trying to simulate natural beaver dams and then also simulate the processes that those natural beaver dams implement on the landscape. And they're pretty cost effective. We like to call them, well, Joe Wheaton actually from Utah State calls them cheap and cheerful. And that is pretty much what they are. So for the most part, they're really cost effective. You just need, essentially I'm going to share really quick. I'll share my screen. Um, where is it? There it is. Just make sure I share the right thing. Here we go. Uh, Hopefully that can be seen, right? And so
Can
ultimately, there's multiple types of beaver dam analogs that we can implement to simulate natural beaver dams. So there's in the upper left here, we have a primary dam or a starter dam, which is really truly meant to simulate the actual beaver dam, the main beaver dam that a beaver would build to create the pond that they would then build their lodge in behind, right? So beaver need to be in water. They feel most protected in water and so that's also why they tend to flood the landscape and have the ponds and the like so they can go in and out of their lodge underwater. They can store their food underwater. But essentially, we attempt to mimic the natural beaver dam. You take posts and pound them in, usually perpendicular to flow, and that with these wooden posts. And then you come in and weave vegetated material. I like to have my engineering students say that they're doing underwater basket weaving, which is a great thing for engineering students to be able to do. But essentially, you weave vegetation in between those posts, and then you pack in mud and rocks and sticks and that to seal it in order to create the ponding environment upstream and simulate that natural beaver dam. And now beavers in general, when they build dams, they don't tend to just build one dam and that they tend to build multitude of beaver dams in series and that where they would then have these secondary beaver dams or what we call secondary beaver dam analogs and that to support the primary dam. So they tend to be a little less beefy. The secondary beaver dam analogs tend to be a little less beefy in size, typically one row of posts, but still weave material through and attempt to seal them to create a backwater that would come up to the base of the main starter dam to help protect that dam from undercutting or from flow that may plunge over the top of it from scouring out at the base and the like. So typically we would put in a single starter dam or primary dam and then two secondary dams immediately downstream in order to act in series to protect the primary dam, right? And then get that ponding function and that natural process function to actually work. We also can use other types of beaver dam analog structures to help just overall reduce stream energy. if we think about a incised straightened channel, so like maybe a farmer has come in, pushed the channel over to the edge of the valley, straightened it, it then creates big stream energy inside that straightened channel, becomes like a highway, right, moving down the valley. And they may have done that so that they could get access to the floodplains to be able to use for agriculture or whatever, right? But it happens a lot, and so that then straightened channel becomes sort of a super highway there. We can add in additional beaver dam analog type structures to act as speed bumps, right? Additional speed bumps to slow down that flow in the river, to back up the water, to introduce more roughness and hydraulic diversity into the channel. And so this could be also similar to woody debris or log jams, and that tend to fall in natural rivers and create great hydraulic diversity and roughness and slow down flow and the like. And so we have these channel spanning beaver dam analogs, which is in the right photo here, that are meant really just to provide roughness and slow down. These are not sealed; they are weaved with material, but we don't pack them with mud and so on and so forth. They're not meant really to pond. They're really just meant to slow down the flow, or even maybe force flow around to widen the channel, which can actually help with depositing sediment. And then the last type of structure that well, there's two more, I guess. One that we're tending to use a lot here is a constrictor dam, which is, and you can see in the plan view here, you build it out 3/4 of the way across the width of the channel. And its primary purpose, still built with posts and weave material, but the purpose is to force flow out into the opposite bank, to make it erode that outer bank to increase channel sinuosity. Because remember, these channels have been straightened. They're pretty straight. So if we want to get a meandering pattern back into that channel or have it help with that, we can use these, what we call constrictor dams, or sometimes they're called deflector dams, to force flow into that outer bank and create that erosion and maybe promote more channel meandering. And then the other thing would be is that is creating an introduction of sediment by that erosion of that bank into the channel. You would put these upstream of a starter dam so that sediment that gets eroded from that bank actually gets trapped behind the starter dam and starts to re-aggrade the channel, raise the channel bed back up so that it can then reconnect flow to the floodplain, and then also raise that groundwater table back up to feed vegetation that we might be putting in that floodplain too, to help grow and the like. So we can use all of these structures in series. There's one other type that I don't have a picture on the slide here of, but it's called the post-assisted log structure, or a PALS. And those are really meant to truly simulate a log jam out there. So they're like piles that can be put right in the middle of the channel, and built up with logs and posts to hold them in place, and that, but essentially simulate like a log jam that's happening and provide more hydraulic diversity and the like. So these are beaver dam analogs and different types of beaver dam analogs. This is on my primary research stream, which is called Thompson Creek, and it's just outside of Spokane, Washington, and it feeds right into Newman Lake. And Newman Lake, right downstream, has a significant phosphorus problem with respect to toxic algae, and algae blooms that happen. And so this Thompson Creek that's going into the lake provides 46% of the phosphorus going into the lake. And so our goal with these beaver dam analogs is to attempt to create this, and it's been straightened and incised, and so to put them in to create the speed bumps, to create the ponding, to trap sediment and phosphorus that's attached to that sediment so that it gets accumulated inside these ponds and doesn't make its way down to Newman Lake. But then also the vegetation in the surrounding area here, we're planting vegetation as well, can uptake that phosphorus and actually use it rather than just have it being transported straight down into Newman Lake and continuing the problem. So we're doing this project in multiple phases, but these are the different types of beaver dam analogs that we're using to do that. And I just talked a lot, but there we go.
Yeah, just a quick follow-up. Are these things that have to be reconstructed every year? Or are they able to last a while, or do you have to reposition at different times? How do
So
you approach that?
yeah, I'm sorry. Yeah, thanks, Joe. The ultimately adaptive management is necessary. So we go out and monitor and sort of see how they're doing, and the like. Now, natural beaver dams are not meant to, like when beavers build their dams, they aren't meant to last forever either, and the like. And so the goal here is they could require some maintenance each year. Yes, if you want to maintain them, in to meet their primary goal, because sometimes, like we've had one like this, like a starter dam, that the flow is actually flanked around, it's gone around it rather than creating the pond to create the pond to back it up. And so it's gone around. But in that case, it's still doing a good job of widening the channel. And like, so it's still forming a good function. And that, so we may just go in there and try to just stabilize it, but maybe have it work as a different function of ponding, change it to being one of these constrictor dams instead. And that, but that does require overall monitoring. Usually each year we go out and double check on what they're doing and how they're doing. And actually I have an ongoing monitoring process for this particular one to see if we're meeting those goals of phosphorus reduction and the like, and sediment accumulation. And then based on those results, yes, you can go in and maybe pound some more posts to restabilize, or even add additional structures if we feel that more are needed. And so we are going to come out to Thompson Creek and do a phase 2 in this reach, because we feel we need some more structures in longer space sections that where the current BDAs are spaced too far apart. We want to come in and put a couple more structures in to try to help promote that natural processes of slowing down the flow and trapping sediment. So yeah, they do require ongoing maintenance, just like beaver very much maintain their dams consistently in that. And so they do require that, but there is some flexibility in that they will still provide good function, even if they're not 100% built as the way they were originally, right? And that, so it still introduces good stream process no matter what, but yeah.
Yeah. Well,
Mm.
I had another question that I think you just started to answer, which was how do you know how many and where
Mm.
to put these, and when do you know that you have to go in and put the different types and at a certain interval?
Yeah, and so this is a good slide to show. Essentially, it sometimes it can be a little bit more of an art than a science. And also the more the better, and that you can put in there within reason to the amount of money. Yeah, I mean the budget constraints and the like that you can put in. And so really you're trying to identify the locations because beaver aren't there to constantly maintain them. You want to try to make sure you design them and place them in locations that you feel the stream power won't like try to take them out, like in more sort of mild sloping locations and the like, or maybe where there's a little bit better channel floodplain connection based on the type of structure you're going to put in. But essentially, it comes down to the goals that you're trying to accomplish as well. And so in this, I know this is a funky looking, colorful picture here, but in the layout, this is Thompson Creek, right? And flows going from top to bottom in these images. And Newman Lake is just down here at the bottom, off the channel, off the picture here. And really, what I did to originally try to figure out what type of structures and where we might want to put them is I created on the left-hand side here, which is a relative elevation model, which is really just a LiDAR data. So you can get LiDAR of the stream, which is a laser scanning of the Earth's surface, and it produces the topography. So it shows you the natural ground topography and the channel topography. And then using what's known GIS, if you import that into GIS, and you can sort of color code the elevations. And then based on that color coding, you can get an idea of where the really low spots are, where the really high spots are. And ultimately, it can also highlight maybe old relic side channels that used to be the LiDAR, that the LiDAR has picked up, that used to be like a secondary channel that might be out in the floodplain before the river was like incised and downcut and no longer connected to its floodplain. So we might use this type of thing to look at this and say, all right, on this image, here and down the middle, the blues are very low elevation and the pinks in this image are very high elevation or much higher elevation. And so you can see the main channel of Thompson Creek is running right down the middle here. When they excavated it and straightened it, they left some natural levees on either side of the channel. And so the channel itself, the water itself in the river has a very hard time breaking out into the floodplain. And that because it's got these sort of natural levees running along it. But you'll see out here in the floodplain, this dark blue these darker blue segments used to be side channels that the river did access prior to when it was straightened and the like. And so using this kind of imagery, I can take a look at that and say, all right, there's this, and on the right-hand image here, here's the structures we placed, right? So the green were channel spanning, the black's one of those deflector dams that are meant to force flow into the opposite bank and so what I did to, just as an example, to help place where I would put that constrictor dam, right? It's based on, oh, well, if I could get water forced out here in and reconnect that old side channel, that's great habitat. That's great energy reduction for the channel. It's great. It can improve wetlands and that out in that side channel. So I position that constrictor dam in that location to hopefully maybe try to force the flow out, to pile up a bit, and then also force the flow out into the floodplain at that location to hopefully maybe re-engage that side channel, right? So that's an example of maybe where I would put a given constrictor dam. Otherwise, with the starter dams and the secondary dams, it's really in locations that hopefully are a little bit milder sloping, because we don't want to have to fight too hard against Mother Nature's process.
Hmm.
And if it is a really deep incised channel, that's a lot of stream power pounding on that dam, on that starter dam, and so you look for a little bit milder sloping sections or segments of the river to put in the starter dams to get the ponding, with the secondary dams in support of that, and the like. And that's where these two sets of starter dams and secondary dams were located because of that, as well. And then a third one down below, in the downstream end tier too. And then really the channel spanners and other types, it's trying to look at long sections of river where there isn't maybe very much roughness, right? Where
Hmm.
it's really like straight and smooth and the like. And we'll come in and say, all right, well, let's put multiple channel spanners or pals, mid-channel pals, in there to really beef up the roughness and then slow down the flow in those locations to create those speed bumps. So I mean, and sometimes too, it takes, all right, well, I can do this all on paper. And my engineering students help me a lot to design these projects in my senior class and my senior undergrads. And then we go out in the field and we walk the stream, of course, too, and say, oh, yeah, we want to put these here. And then based on the natural vegetation that's out there and what it looks like and how also easy it is to get the post pounders in and the like to pound in and build the structures, we may make some adjustments in the field, to actually put them in the ground then too. And that
That's
based on
awesome.
actual field conditions. So it's a combination of sort of desktop design, and hydraulic design, and then field design too, when you actually can see where you can put it.
Yeah, very
Mm.
cool. So I also want to ask you about what is a stage zero channel network?
Ah, yes. I'm going to stop sharing for a second.
Yeah.
All right. So stage zero, uh, what is it? Brian Clore and Colin Thorne wrote a paper in 2013 that's called the Stream Evolution Model. And it was building off of previous channel evolution models by like Simon and Hupp and Stan Shum, from long ago. But essentially, the premise of this stream evolution model is that you have a given natural river system that experiences a disturbance of some kind. Maybe it's a straightening, right? Like what we just saw in Thompson Creek or whatever. But in that disturbance, after that river's been disturbed and now it's in its new form, it will attempt to work its way back into its original form or into a new, more stable form. It's adjusting essentially, constantly adjusting and changing. And so the stream evolution model is a cyclical, evolution of that channel adjustment. And Clore and Thorne discovered, well, for a long time we have been assuming that most rivers are single thread, right? That they're, like we just saw in Thompson Creek, there's one river reach that's running down the valley, right, as a single thread system. And that Clore and Thorne made pushed that a little bit, pushed back on that a little bit, and said, well, there is a lot of pre-disturbance. There's a lot of evidence and research evidence and former evidence from photos, so on and so forth, that say there's actually these types of anastomosing channel networks out there, which are multi-threaded systems. And that where the river spreads not just one single channel, but it spreads out into multiple channels, right, as it moves down a valley, and the waters just sort of spread out. And in an anastomosing system, and they so essentially they called that a stage zero because the previous evolution models started at a stage one, right? So the previous ones were stage one through stage five or whatever as the channel adjusted, right? And only included that stage one through stage five in the previous evolution models were only including single threaded channels, like one channel down the valley. Clore and Thorne said, well, there's actually this pre-disturbance condition. And this was actually, we had a whole lot more of these multi-threaded systems on our landscape when we had a lot more beaver as well. So a beaver meadow, when you have beaver that go into a large valley with a river running down it and they start to dam it up, they create these multi-thread channels, right? They spread the water out all across the floodplain, all those dams, like the series of dams and that's like a stage zero condition, right? Before any disturbance or before we remove the beaver from the system, right, by eradicating them. and that we had these sort of in these wide valleys in along the river network, we had these valley systems that had the river spread way out, valley wall to valley wall, and multi-thread with a lot of vegetation, sort of keeping those multi-threads in place, but spreading it out and moving it around and that. And so a stage zero is ultimately in the right locations. You couldn't really have a stage zero multi-threaded anastomosing system in any location, but usually in these broad depositional valleys, wide valleys, in that can allow the water to spread out, and the like, that these systems are super high in biodiversity and hydraulic diversity. They provide significant habitat. It brings the groundwater table to the surface to feed the vegetation, and that. So they're super resilient systems that can absorb a lot of flow and sediment and nutrients and provide really great habitat, and biodiversity for the wildlife that's in that surrounding area. So Clore and Thorne are saying that we could potentially, if you have this disturbed system, it's possible and to take it either back to stage zero, and that so through restoration practices, and there's a multitude of ways we can use beaver dam analogs to do it, and that it just takes a little bit more time by simulating the beaver dams, right? Because ultimately beaver dams can lead to a stage zero anastomosing system, and that. But so we could use beaver dam analogs. It just takes a lot longer because it's natural process. You put in the structures, and then you have to rely on Mother Nature to have the water and the sediment coming through and all of that. So, and that, or you can come and, like, say in Thompson Creek, you can make a stage zero system right away by bringing in big, heavy front loaders and equipment. And based on that relative elevation model I showed a minute ago, if you have anthropogenic high points like old levees, and that in the valley, or old roadways that came across that are no longer in existence, but you have these big piles of dirt that are left over from that, you can find a way to balance the cut and fill essentially, but you would come in with big bulldozers and the like and move all that high or that high elevation sediment, push it into the channel, fill the channel in, and let the water just spill out across the whole floodplain, right? And become that stage zero again. That's quicker than letting beaver dam analogs do it, and that for you. So you can have that done in a year of contracting work, right? And you get an immediate response, but it's a whole lot more expensive, right?
Hmm.
To do it. And they call that a full valley reset, and that to take it back to a stage zero. The other option is you can also have it go around to what's called stage 8, which is a new anastomosing system, but sort of built inside the single threaded channel. So you have a single threaded channel, it will start to downcut, right? Because the energy is so high, and that in the system, the shear stress, it'll erode away the bed of the channel, and it'll start to downcut. That will then lead to that stage 3. To go to stage 4, it'll start once the channel banks get really high, they become really unstable and they start to collapse in. And so
Hmm.
then that starts to widen the channel. And that widening, though, once it reaches a certain point, stage 5, stage 6, and that in the stream evolution model, when it widens enough, energy is reduced, and you start getting channel sediment building up again inside the channel, and then it forms a new channel inside the old one, right? But it no longer is connected to its original floodplain. It starts creating a new inner floodplain with a channel inside of it. And then eventually that keeps going, and it could turn into an anastomosing system inside the old channel, right? And that's a stage 8, which is still has really good diversity. Like, it has all the good hydraulic and ecological benefits of a stage 0. It's just in a lower inset channel and a smaller valley, I guess, because
Hmm.
it's inside the old channel. But yeah.
So when you're doing your restoration, how do you decide if you're trying to do a stage zero channel network or this full valley reset, or just notionally, if you're doing a full valley reset, how
Yeah.
do you decide where you described kind of the cut and fill of different things, and like
Yeah.
how do you decide where to start, and are you deciding how many threads, or are you doing one intervention and then letting the threads be illuminated, or something
Let
like
the
that?
threads be illuminated, indeed. Yeah. And so the goal is to just get the water to spill out completely across the valley. So
Yeah.
it doesn't have an initial like channel to go into. And you do that too by, well, to figure out the cut and fill stuff, we can use that relative elevation model and another thing called the geomorphic grade line, which is maybe a little bit too much to get into right now. But ultimately, you're trying to find where are the high points, where are the low points, accentuate them off that LiDAR data, and then you already know the main channel is the really low point, right? And so then where are the high points that are maybe anthropogenic, like that weren't there in the first place, right? Can we
Mm,
grab those and move them and fill in the channel? And so there's sort of a science as well as an art to balancing the cut and fill so that you don't have to truck in a whole bunch of fill, right? Or truck out all of this cut that you can't use elsewhere.
mm,
But the goal would be to then fill in that channel. And then really, you have to then also come in and add a ton of vegetation. You have to add a whole bunch of wood all across the valley. And that has to come in, however you can get it in there. But ultimately, you have to create roughness, a big diversity of roughness across that valley. And then you just let the water spill down the valley or spill down it again. And based on all of that roughness and then the topography that's now created, the water will start to move on its own. It'll create its own multi-threads. It'll create pools here. It'll create riffles there. It might move the wood around a little bit, but that's okay too, and the like. But realizing it, because the water gets to spread out across the whole valley with all that roughness, it's pretty low energy. So
mm,
it really is going to want to just slowly move around and stay put and then create pools over here and riffles over there and a thread here and a thread there. But it's not a high energy system that's going to try to be like scouring everything out, right? It
mm,
really wants to be more depositional in that dropping sediment and like leaving sediment in piles here and there. Great for salmon, for spawning, so on and so forth. So it's creating sort of a low energy environment that's wet all throughout. And it's really actually pretty cool because it's resilient. It builds resilience into the system. It allows, because then that creates both also that as well as if we can use beaver dam analogs to recreate, say, a beaver meadow type situation with simulating those beaver dams, that also creates resilience because it allows the water to be absorbed and contained and held on to, right? And a much lower energy system is, I think of it as both stage zero valleys as well as beaver dam analogs and beaver meadows as big sponges, right? It just traps and holds that water and then releases it slow over time too. So they're even like the Methow Beaver Project is they spent a lot of years now trying to reintroduce beaver, right, back into the Methow River in central Washington. So sorry, the Methow Rivers in central Washington in the Methow Valley. And they have been trying to either reintroduce beaver to get them back out in the Methow River watershed to build dams and store water and hold on to it longer. Or now they're also implementing a lot of beaver dam analog projects as well to try to simulate that as well, because the snowpack. So thinking about climate change and so the snowpack in the North Cascades and that feed into the Methow River that comes down through the Methow Valley, the snowpack's diminishing, right? And that timing changes, or it's going to even translate maybe into rain rather than snow, and so if we can get more sponges or storage from beaver dams or from stage zero valleys and the like and stuff up in those watersheds, that can hold that water longer, right? Because typically, if we were to translate from a snow dominated system to a rain dominated system, the snow is held on for a lot longer, right? And then that's the timing of that is the snowpack melts and is released in late spring, early summer. And then maybe even further, if there's ice and glaciers and such in there, and there are in the North Cascade, then you get even that water releasing even later into August, when essentially in that side of the North Cascades, it stops raining, right, in
mm,
August, and that gets really dry on the east side of Washington. And so if you can have the beaver dams or the stage zero valleys out there storing that water when it happens, when it either runs off as snow or if that snow starts turning into rain with climate change, that's a much quicker runoff, right? You don't get the storage from the snowpack anymore. It's just going to run off right when it rains. So if you can get those back in there in those storage areas in there to hold on to that water longer and release it slower, you can better simulate that existing sort of snowmelt regime, right? And then feed the water down into the system when it's really dry later on. And so all of these like sort of things are really good for building resilience, and in particular in the light of climate change and the uncertainty that goes along with that, if you can allow the river to absorb that water, or even then also give rivers space to move and absorb and not sort of be locked in with infrastructure all around it and so on and so forth, right? If it can essentially have more room for the river and the like in those big valleys, or slow down the flow and create more depositional environments, it's better for resilience in managing those climate change uncertainties.
Yeah. Well, you've spoken to this a little bit, but I wonder if you could talk more about this is kind of a high level question. Why is stream restoration important, and how can we do it better as a society at scale?
Yeah, and so essentially stream restoration restores natural structure to a river, right? And typically we're coming in to restore a river that's been, yeah, highly manipulated, in that, or even partially manipulated in that. But like I said, with Thompson Creek, and we see a lot of these streams, particularly in Eastern Washington, straightened and ditched so that they can have access to the floodplain to farm or to build or to whatever, and that. But that significantly reduces water quality, significantly reduces habitat, right? So the purpose of restoration is to go in if it's possible to do it, and that go in and improve water quality by instead of having that phosphorus and sediment just shoot straight through Thompson Creek into Newman Lake, let's bring in some roughness and some elements to slow that down and trap it and retain it so that the vegetation can uptake the phosphorus rather than have it impact downstream Newman Lake, right? So improve water quality, create habitat for fish, macroinvertebrates, or the bugs in the channel, right? And other wildlife and stuff. And then also we can help with flooding impacts, right? If we can reconnect certain sections of the river to its floodplain in spots where there is space to do that by restoring floodplain connection. That creates floodplain storage, which can reduce flooding downstream, right?
Hmm.
In environments downstream. So there's like flood mitigation. So essentially improving water. So restoration is important for improving water quality through filtration, reduced sedimentation, and that it can keep sediment and help a better flux of sediment through the system, a more healthy flux of sediment. Nutrient cycling improves biodiversity and habitat. Like Thompson Creek has very little habitat for the fish and the bugs that need to be able to have places to hide, need to have their own food to eat, right? So organic matter and the like. And so we can help improve. And I am also in the Pacific Northwest, and so habitat and fish habitat, particularly for salmon, is extremely important. And a large number of our restoration projects that are completed in the Northwest are their primary goal is to improve habitat for fish, and in particularly for salmon, and that so that they can do their migration and they can spawn and they can and that be remain that food source for indigenous tribes and so on and so forth, right? So improving that habitat and biodiversity is pretty important. It's important everywhere in that, but it is highly important here in the Northwest as well. Yeah, and you can improve floodplain function, infrastructure, and property protection if you have different spots that you can do the restoration that can help reduce flooding downstream and the like. It'll improve recreation for fishing, like fly fishermen, right? So on and so forth, boating, all of that, right? So aesthetics in general and just the social aspect of getting people to the river, right? They would much rather come to a beautiful meandering river, and that's got lots of habitat and biodiversity in it and fish to catch than currently Thompson Creek, which is essentially a ditch straightened channel.
Hmm.
And that so did that help? Did that answer
Yeah,
your question?
yeah, and just a follow-up, how do we do this uh, better and at scale as a society? Is it at the community level? Does everybody take ownership of their stream, or is there how do you see that working now or in the future?
Yeah, I think it could be at any scale in that for the most part. I think communities very much can play, like even at the local community scale, like your little stretch of river that maybe the kids go out there and dam up with the rocks like I used to do when I was a kid, right? And that, but getting community involved in it too through like citizen science and the
Hmm.
like and having that uh take ownership and stuff. So we've done that at the scale of like if a restoration project is done at a very small scale and in a local community on a short reach or whatever, you can get the community involved by helping to monitor, right? And so they can come out and just collect the bugs that they see, and then there's ways to sort of, I guess the word's educate the community for citizen science, right? So that you can teach the very easy ways to teach to say, all right, we're collecting these bugs. Here's what you should be looking for. Here's what you should document. Here's what you can do, and the like. But at least getting involved at the community scale is great in order to have that attachment, right? That local attachment, plus also the community can help set goals, right? Restoration goals for that particular reach based on how they use it, how they interact with it, and the like. And so, yeah, I mean, it can happen. Restoration can very much happen at the small scale, community scale with a lot of stakeholder involvement. there. And then it can also happen out at the watershed scale and stuff too. So there, sometimes the watershed scale, maybe it comes down to the different communities that are within that watershed establishing, like, say, stormwater management ordinances to control stormwater runoff, which if the runoff that's not from impervious surfaces, right, in the watershed, if it's not controlled or managed, it can highly degrade stream systems in that watershed. And I guess in a way I say that is job security for river restoration practitioners and that to keep going out and looking at that. But at the watershed scale, if those kind of ordinances can be implemented and then stormwater management practices implemented, that at the watershed scale, that can do a great number of things for river restoration and for restoring rivers and stabilizing rivers within in the watershed itself. So yeah, at scale. So I'm saying, yeah, pretty much it can happen at almost any scale in that. What tends to happen, I would say most is it tends to be at the reach scale. And it is typically, there are usually a lot of stakeholders involved in a river restoration project, but it tends to be consultant firms that will come out and do the analysis and the surveys and then come up with a design with a lot of input from stakeholders such as public agencies and private agencies and local community stakeholders and the like nonprofits, right, so on and so forth, to develop that. And then they would then go out and implement. Well, you have to go through the regulation process and stuff too. So there's permitting agencies that make sure that things are being done that meet, say, the Clean Water Act and that. So the regulatory side of things, but you work through the regulatory process too to then implement your project and the like. And so it tends to happen most that way, but it can happen at a variety of scales.
So my last question is, what do you see as the future of this research, and do you see any, or are you pursuing any breakthroughs or discoveries related to your research?
Yeah, so really, I think the future needs to be and is leaning more towards resilience. In that, which I said earlier, and that because of climate change and it is so much more challenging now to predict and understand what rainfall events are going to look like in the future, like the hydrology that feeds into the water that's in the rivers, right? And then how do we design accordingly for that? And with the uncertainty involved, it's really hard to know. And so the key is like, okay, how can we, from an engineering standpoint, I say, how do we build in factors of safety, right,
Mm,
into that river reach, which would be essentially resilience. So give the river space and give them room and try to plan that into your restoration designs, right? And then also have it be a process, or what I call process, well, not I call it, but we are calling it process-based restoration. So you're, instead of just taking a channel and building it and then locking it in place and saying, oh yeah, it's connected to its floodplain and it's meeting these goals, but if it doesn't have the ability to continue to adjust and move, right, then that's much less resilient and the
mm,
like, and more likely to fail, especially under the uncertainty of climate change. So process-based restoration is looking at the natural processes that are happening, what the river's already doing, and then enhancing those processes to enhance them to support maybe floodplain reconnection or restoring the river, and that in the proper direction rather than what it's currently doing. So thinking about upstream and downstream impacts and the like, but giving it natural processes, things like sediment movement through the river, the actual flow of water through the river, and what kind of hydraulics, uh, shear stress, and erosion capability that water has. And can we help manage that, right? And stuff. So have it happen in locations where maybe it doesn't have an impact and the like. So manage those and allow floodplain connectivity. That's the big thing is we must reconnect our rivers to their floodplains in that.
mm,
And we've spent too long and far to reduce that because we want, and it's a natural tendency. We want to build houses right up next to the river because it's a pretty view, right?
mm,
And you want that river right on your back door, or we want to do farming. The floodplains are super rich and fertile because of all the sediment that had been dumped on them over the years when the river was connected to the floodplain, right? We want to farm them and that because it's great soil for farming. But then when you don't allow that river to get out there and flood, you're creating a big, yeah, super highway of water, sediment, nutrients just cruising through there and eroding and causing a reduction, decrease in the groundwater table and so on and so forth. So the idea is we want floodplain connectivity. And I think that's a big future is getting our floodplains back again and
mm.
allowing the river to use them. But it is a challenge because, like I said, the floodplains are super beneficial for many things that we already like to do with farming and with yeah, and with infrastructure and so on and so forth. So and that, so if there's ways that we can, yeah, set back and get that floodplain back and get the river reconnected to it, it would be better overall for everybody and for every living thing that uses that river, I guess. So
Yeah.
process-based restoration is big into the future, floodplain reconnection for sure, and then any kind of resilience and space and room that we can give that river in our restoration designs will be highly beneficial, with particularly in unknown with climate change.
Yeah.
Mhm.
Well, Sue, thank you so much for taking the time to share your research and your
Sure.
insights. And I hope we can continue the conversation down the road.
Yeah, that would be great. I appreciate it. Thanks for your time. I appreciate being on here.